All right, well, let's start reviewing a little bit to kind of get us into what we're dealing with today. Remember, we left off yesterday showing you this picture, I think, and yesterday we talked about which one were we talking about yesterday? Yesterday we talked about reflection, right? And we did a little bouncing ball game into the bucket, right? And we had double or nothing. Sorry, Lewis, about that double or nothing. But we had the double or nothing on that. And really, we learned a couple different things. We learned about the two different types of reflection, regular or specular versus diffused. But one of the main things we learned was that the incident angle in, was equal to the angle out. I remember that yesterday. Angle in was equal to the angle out. And so we had that, and that was hopefully pretty straightforward. Today, we're shifting to refraction, right? And really, the rest of the unit is going to be refraction. And so, when we're dealing with refraction, one of the big differences, the angle in is not equal to the angle out. Okay, the incident angle of the light wave is different than the refracted angle. That's what refraction is. And we're going to talk about why, and we're going to get into the equations and get into some specifics and do at least two examples before we're out of here today. So we were kind of laughing at this picture here yesterday, but has anybody ever seen something like this happen before?
Yes. Oh,
No, I'm serious.
yeah.
Where? Okay, in a pool, right? Maybe somebody's half in, half out, or if you've ever seen somebody like in a shallow pool where their feet are just in the water and it looks like their feet are like shifted over to the side, right? Depending on how you're looking at it. Any other examples of this? What's that? Yeah, if you've ever put like a pencil in a glass of water at an angle, right? It kind of looks like the pencil is shifted, the bottom is shifted over, right? Do you have an example?
I was gonna see like a dolphin. I don't know if you ever seen like the dolphin show at the zoo.
Okay, good.
When they're like about to get out, it's like half their body's like over here.
Awesome, right? That's a great example, right? The dolphin show, right? If you see the dolphin, because I think they have like a clear, usually they have like a clear tank, and so you can see them underwater also. And as they're coming up, it's like they're shifted a little bit, right? And so the reason that this happens, right? Or if you've ever tried to like scoop a fish out of the fish tank, and it's like not exactly where you thought it was going to be, right? With your little net or whatever the case might be. That's another example. Unfortunately, I think I killed our last fish trying to get it out of the fish tank.
How do you kill it?
Well, I couldn't catch it, so I just like dumped them like into the other bowl, and I think after I dumped them, everything kind of went downhill from there. So Mr. Bubbles wasn't producing bubbles anymore, and so that wasn't cool. But now we have like one of those little mechanical fish, like the aquabots. We just got like a mechanical one instead, so it doesn't die, right? And so now it's battery powered. So that's good. And we call it Mr. Bubbles also, so it's kind of like Mr. Bubbles back in a robot form. And so but if you ever tried to do that, that's another example. Well, why does that happen? Well, remember what we said yesterday when we had that mirror up here? When you were getting your reflection off of the mirror, the light waves are coming off the lights and off of you and then off of the mirror and then into your eyes. All of that is going through the same medium. Okay, and that medium is air. All right, it's not changing. Well, if we're looking at this guy, and I feel kind of uncomfortable talking about this guy's chest, we'll call it a torso. Somebody said last year, let's just call it a torso. That makes me feel better. Okay, so we're looking at his torso. Okay, it's kind of weird. All right. So anyways, so if we're looking at this part here, well, what's happening? We're getting light waves from the source, from the sun, who's outside or whatever, and it's hitting his body. Those light waves are bouncing off of his body in all different directions, but the ones that we see in our line of sight are coming through the water, and then through the air, and then to our eyes. And so what we have is we have two different mediums that the light waves are passing through. Okay, they're passing through the water, and there's actually probably some glass or some plastic here, and then there's the air, and when it goes through those two different mediums, some things change about the light wave, okay? And refraction occurs, all right? When you're looking at the dolphin in the dolphin show, right, you're seeing that dolphin through different mediums, right? You're seeing it through the air, you're seeing it through the glass, you're seeing it through the water, there's the different mediums, and when that happens, and when you see it at an angle, that's when refraction occurs. Okay, refraction is when light waves bend as they go through different mediums. Okay, so here's the definition. Oh, here's an example. This is, I used to kind of set this up in class, but I just found this was a little bit easier. And so this is just a light source, right? And I don't know if you saw it or not. That's a black line or a black dot. Let's erase that. Right? The light source is just shining a beam of light. He's going to take a block of plastic or a block of glass, and you can see that when it hits that boundary, the light gets bent. Okay, and if you can imagine the guy in the pool, right? All those light waves from the guy in the pool are coming through the water, and when they hit that new medium, they get shifted over and they get bent, and that's why the part of the body that's above the water that's not getting bent looks different than the part of the body that is in the water. Okay, and that's true with all of those examples that you guys just gave us. That's called refraction. So we need to go here. There we go. There's our definition of refraction. All right. What you guys just gave me examples of, and what we just talked about. Refraction is when waves change direction as they pass between two media at an angle. Okay. When waves pass from one medium to another, air to water, air to glass, air to plastic, whatever the case might be, refraction occurs. Okay, the light waves get bent or shifted, or the angles change. And the big reason why, the speed changes. The speed changes. What's that? It's going to slow down, right? So I don't know if that's what you mean by become weaker. It might get a little less intense also. So those examples: thermometer, beaker, glasses, mirages, shallow pools. If you've ever seen a mirage, who knows what a mirage is? The mirage, right? A mirage is like when you're driving on the highway and off in the distance, it looks like there's like some water on the road, and then you get up there and it's not there, right? They have it in movies sometimes where they're like walking through the desert and they see water ahead, and then when they get there it's not there. They kind of play it up in movies a little bit. But that's an example of refraction also, because the light waves get bent off in the distance like that, and you're looking at them at an angle, and they get bent because right close to the surface of the sand in the desert or on the blacktop on the highway, the air is really hot. And so the temperature of that air is really high. And then as you get off of the surface, the temperature there decreases. And so it's almost like there's two different mediums, right? There's two different types of air, really hot air and then normal temperature air. And when the light waves go through those, they get bent, just like we talked about, they going from air to glass or air to water, hot air to cold air, right? It can bend light waves also, okay? And so it kind of gives it that strange look, and it bends the light waves a little bit off in the distance, okay? So anyway, that's the definition of refraction. Now, like I said, we're going quickly. I apologize, right? We're going to kind of push through a bunch of stuff today, but every different type of material that light can pass through has a different ability to bend light. That would make sense, right? You would assume that probably water would bend light a little bit differently than plastic or than glass, okay? And that ability for different objects to bend light, it's called the index of refraction, okay? This is like the bending power. The index of refraction tells you how much the material is changing the speed of light. And again, every transparent material has a different index of refraction. We're gonna do a lab either Friday or Monday, where we're gonna be able to calculate the index of refraction pretty accurately of glass, plastic, and water. Okay, you're actually gonna measure that and visually see how that works. It's a pretty good lab, I like it. All right, so we have our equation here. In order to find the index of refraction, which is lowercase n, the bending power of the material, here's what you do. You divide the speed of light, you divide the speed of light by the actual velocity of the material. We want to know how much the velocity changes. Remember we said refraction is based on a change in velocity. And so this ratio tells us how much the velocity is changing. If the velocity changes a lot, the index of refraction is going to be high. If the velocity barely changes, then the index of refraction is going to be low. So that c is the speed of light. What number is that? We know that number. 300 million, right, meters per second, or 3 times 10 to the 8 meters per second. So we put that in the top, and we put the other velocity in the bottom, the actual velocity in the bottom. And there might be a problem where they just ask you to calculate the index of refraction. You only need one number to calculate the index of refraction. You only need the velocity of the material, because you always have the speed of light. Okay? Since nothing can go faster than the speed of light, n can never be less than 1. So if this comes out to be a decimal, you probably flip-flop them. You probably did something wrong. Okay? And then the index of refraction in air is very close to the speed of light in a vacuum, so the n value of air is usually we just use 1 for the index of refraction in air. So far, so good? All right. Let me take a break for a joke. I have a joke I told my first period class. They didn't really appreciate it, but I'll appreciate it. All right, what is Forrest Gump's password on his computer? One Forrest one.
Say that again.
One Forrest one. Like run, Forrest, run, but one. Somebody told me that before first period. I had to tell my first period class, and they like all wanted to leave.
That's first period though.
Yeah. One more. I got one more.
I know, they're freaking me out.
What happened?
Is that for us?
Yeah.
No!
This is easy. This is easy. We'll go through this now. All right, one more. One more joke. I just overheard somebody say this today too. What did the duck say to the cashier when he bought lipstick? What? Put it on my bill. All right, so save your jokes. We're gonna have some time in the dark room. We're going to the dark room. We're gonna have some time for jokes. So save some jokes there. All right, here are some. All right, here are some common. Right, some common n values. Remember, these are n values, index of refraction. These are some common n values for materials. Okay. Air is 1.0. Water is generally 1.33. Glass is 1.5. Quartz crystal 1.54. Glycerin, which is like a plastic, 1.47. And diamonds, 2.42. You don't need to memorize those, but I would write them down so that you can use them as you're doing your practice problems. Most often we'll give them to you, or you'll have to find them. In the lab, we're going to have to use these a little bit, but it's probably good to know what diamonds. And we're not going to use diamonds. Not quite in our budget. But it's interesting that you mentioned diamonds. We're going to talk about diamonds in a couple of different ways this unit. But diamonds, obviously, right? Pretty rare, pretty expensive. I didn't know much about diamonds at all until I bought my wife's engagement ring, like way back when. And I was like, like overloaded with all the information that you have to figure out before you buy a diamond. That's crazy. Cut, clarity, color, very good.
I always want to say cost.
The cost is like a given, right? But anyways, you have all these things. But here's the deal. Diamonds are special for a lot of reasons, but they're transparent, but they're also very dense, okay? They have a really high density for a transparent material. What that means is they bend light a lot, okay? So when light hits the surface of a diamond, it bends it at a very, very high level, more than any other transparent material. And when diamonds like sparkle or shine, right, when light's passing through them, that's for two reasons. One, because of the way they cut the diamond, but two, because it bends the light a lot, right? Like traps the light inside the diamond, and like sparkling before the light passes through. So anyways, diamonds, we're not going to use them in the lab, right? But they bend light quite a bit. All right.
Somebody said that after you.
Nobody said that after. All right. So here's what we're going to do. When we have refraction, as we said before, this is like one of the big differences, right? When waves are refracted, the angle of incidence does not equal the angle of refraction. If this was a mirror, right, that angle in would equal the angle out, right? So that's not happening anymore in our examples. This is refraction. Now the light wave is hitting the boundary. This would be air, and this would be water or plastic or glass or diamond or whatever. That'd be a big diamond. But as the light wave hits the boundary, now it's going to pass through, and these two angles, we call them angle 1 and angle 2, theta 1 and theta 2. Those two angles are not the same anymore, okay, because it's being bent, right? The light wave is shifted, right? And that's why we saw the guy in the pool look like he was shifted. That's why the dolphins look like they're shifted or whatever, because the angles don't equal each other. Because you have to factor in two things: the end value of the materials and the angle at which it's entering. All right. So when we have problems like this, we're going to set up like a little XY axis here, and we're going to measure from the normal. That dotted line is called the normal. We're going to measure the angle from the normal to the incident ray, and we're going to measure the angle from the normal to the refracted ray. All right, and we're going to see how much those changed. And there's a pattern that we can develop using this equation that you guys are excited about. Right here, okay?
When we're talking about vectors and pre-calculus,
Very nice.
it's scary.
And my daughter still calls vector from despicable me Hector. So. No, we just laugh. So. All right, so are we good with this? We're going to skip this and that, and we are going to. We're going to do a quick example here, okay? And as we said before, this is kind of a clear example, and we're going to use this as our first example to calculate how much the light waves are being bent. So I'm going to go ahead and stop that there. Okay. So here's what you guys can do: is we're going to take. That was the board. All right, we're going to take that, and what I would like for you guys to do is to draw this out. So you don't have, we're not going to worry about, see how it's bending at the bottom there? All right, we're just going to worry about this bend right here, from air to whatever this material is. Okay, I'm going to try to move it in a second. But if you guys could draw the incident ray and the refracted ray, and then draw a little boundary line and a normal line. Okay, that's what we're going to do. Let's see if I can move this at all. All right, so in order to understand the relationship between the incident ray and the refracted ray, we're going to use an equation that's called Snell's law. Okay, this is Snell's law, right? Snell's law is n1 sine theta 1 equals n2 sine theta 2. All right, and maybe I'll put it down here. Right, n1 sine theta 1 equals n2 sine theta 2. Okay, all right, well, let's label what that means. We're going to compare what's happening up here with what's happening below the boundary. Right, so n1 is going to be the index of refraction of whatever the material is on top. Okay, and in this case, what is it? Say it again. That would be air, right? And we already know what that value is. What is that value?
1.
It's 1, right? So we're going to say that that's air, right? And the index of refraction for air is 1.0, okay? We also have to take into account what that angle is. That is going to be, that's going to be theta 1. So if I multiply n1 times the sine of theta 1, it's going to be equal to n2 times the sine of theta 2. All right, n2, right, is down here. This would be, I don't know if that's glass or plastic. Maybe we'll just say for now that it's glass. And what we're going to do in this case is we're not going to use the n value that I gave you for glass. We're going to calculate it. Okay, so I'm just going to put n2 is equal to question mark. That's what I want us to try to find. And this, what's that going to be? That's going to be theta 2. Okay, so if we could either measure or know those two angles, and we know n1 is 1, we can find n2. Basically, in a problem like this, you're going to have 3 out of the 4 things, and you're going to have to figure out what the 4th one is. All right, so that's a black line. We still, after a whole year, not used to this new smartboard. That is a giant protractor. Right? And so I'm going to go ahead and measure angle 1. Theta 1, if I'm going here, I'm going a little bit backwards on the protractor, but that's okay. That would be 10, 20, 30, we'll say 38 degrees. Okay, so for theta 1, right, for theta 1, we're going to put in 38 degrees. You're going to draw it on top of this.
We're going to use the protractor.
So on the test, we're not going to use a protractor. We'll give you the angles. In the lab, we're going to use a protractor at some point to figure out what the angles are, to check our math. Okay. That's also a dot. All right. Then we need angle 2. Don't be too impressed. All right.
Do that again.
That's not right on, but that's okay. So we want theta 2, and theta 2 is going to be 10, 20, we'll say 22 degrees. Okay? We'll say 20.
Actually, 23.
22 degrees. Okay? All right, so let's take this. All right, and let's start filling things in. N1 is 1.0. We're going to multiply that times the sine of theta 1, which is 38. That's going to be equal to N2, which we don't know, times the sine of theta 2, which is 22 degrees. All right, so calculator people, if you could help me, please. We need to do 1 times the sine of 38. Again, especially with this kind of math, with the sine and all that good stuff, I would make sure you know how to do this on your calculator. It doesn't really help to watch us do it. Calculate it along with us. So 0.62 is 1 times the sine of 38. And we're going to set that equal to N2 times the sine of 22. What's the sign of 22?
0.37.
0.37. We need to solve for N2.
So divide.
Divide by 0.37. So 0.62 divided by 0.37.
1.68.
1.68. So the N value that we calculated for that material, which we're saying is glass, but although we don't really know what it is 1.68. And what was the highest value for glass? 1.54 for the crystal glass. So either my giant protractor wasn't super accurate, or that material has a little bit more density than a quartz glass. But either way, we're able to find what the N value was. Okay. The hardest part, I think, of this problem is, well, some people might have a little trouble with this math. We'll help you along the way. And actually, the next example we do might be a little bit more difficult. But lining up N1 and theta 1 and lining up N2 and theta 2, that seems to be a bit of a problem sometimes for people as well. Okay. All right. Let's do one more example, and then you guys will be really ready to go for tomorrow. Well, let's do this one. This one says, and I would draw your little XY axis here again. This one says, hang in here with you guys are doing good. We just have 5 more minutes. One more example. A light wave travels from air and into glass. It hits the glass with an incident angle of 30 degrees to the normal. Yes, please draw it. The glass has an index of refraction of 1.4. What is the angle of refraction? So we know that the light wave is going to bend when it hits the glass. Okay. We want to know how much is it going to bend. Okay. What is the angle of refraction going to be? So I would draw a little XY. Draw the normal. We know that the angle that it goes in at is going to be called theta 1, and the angle that it comes out is going to be a little bit different than that incoming angle, and it's going to be theta 2. We're going to talk more about this later, but whenever it goes from less dense to more dense, it gets bent towards the normal. That's why I knew it was going to be a little bit less, and I drew it that way. We'll talk more about that probably on Friday. So we know that this is going to be N1. That's going to be N2. That's theta 1. That's theta 2. So that's how you set that up. And you got to make sure that you're plugging the numbers in the right spot. And for me, I always recommend a little drawing, even if it's a small drawing, so that you can get the N values on the right spot and the angles in the right spot. Okay?
Can I do it on the board?
Is the second angle the one that's here?
Let's talk about that right now. So we have 2 angles. Theta 1, theta 2. They give us one of the 2. Which one did they give us? So it says it hits the glass with an incident angle of 30 degrees. So it's going to be the first one, right? If it hits the glass at an incident angle of 30 degrees, that one's going to be 30. And then it gets refracted and it gets bent, and this is the one that that's the one we're trying to find. All right, so N1 and N2. N2 says what is the angle of refraction? Which one do we know? Actually, we know both of them. That's 1.0. This is glass on the bottom, and the problem tells us that it's 1.4. Right? Again, if they give you the index of refraction, don't use the one that I gave you. Use the one that they give you. All right, we got to go through this quickly. N1 sine of theta 1 is equal to N2 sine of theta 2. All right, let's move this over a little bit. All right, N1 is 1.0 times the sine of 30.
25.
Hold on one second. N2 is 1.4 times the sine of theta 2. All right? So, what is this?
Is it?
Do you have a question? Go ahead.
Isn't it glass though?
Yeah, so it actually tells you what it is. So there's different types of glass, right? There's different types of glass. Be nice.
Oh, I know.
All right? So, 1 times sine of 30.5, did you say? Yes? That's equal to 1.4 times the sine of theta 2. Now, this takes a little bit of work here, right? So follow along with me, please. We want to get that angle by itself. So first of all, let's divide by 1.4. So 5 divided by 1.4, 0.36. Right? 0.36 is equal to the sine of angle 2. A lot of people want to stop right there. We're not done. They have to get that angle by itself. How do we get rid of sine? And we're going to take the inverse sine of both sides. That's like dividing by sine, kind of, right? So if I multiply that by the inverse sine on both sides, right, this goes away. And the inverse sine of 0.36, 21.1 degrees is equal to that angle. So this angle here is 21.1 degrees. The angle changed, right? It was 30. Because it changed mediums, it slowed down. Because it slowed down, it got shifted, and now it's only 21.1. Okay? The only other real trick that we can do on this is sometimes we won't give you the end value, but if we give you the velocity, right, then you have to go back to n equals c over v, put the velocity in, take the end value, put the end value in there. We just add an extra step. We'll try to do an example like that at some point, okay? Tomorrow, WebAssign, you can work on WebAssign now, and you can work on those practice problems. Like I said, I won't be here tomorrow, but you should be able to have a pretty productive day tomorrow, all right? All right, good job, guys.
Can I last week close? Oh, yes.